So my name is Ross Bagurdes. I was telling you guys earlier, this is my favorite conference to come to. You get to talk to the coolest, nerdiest people that you'll ever meet. I've met some really great friends through this conference, and I'm super happy about it. It's not like other conferences, right? Cisco Live is happening right now, and this is the better conference. You'll learn more here than you would at that party, right? That's just a party so they can sell you more junk. Here you're going to learn how to do something. In fact, somebody was just telling me a story how they used the information they learned at SharkFest the last time to go prove a really arrogant engineer that he was wrong. It's like, yeah, that's what we need to be doing. So what my role is in life now, I've been an engineer for years. I started off actually as a structural engineer. That's my degree and my background. And but that was in the early to mid 90s. And right when IT and business was kind of like, they're fighting each other. There was an IT department sometimes. Other times they just left it up to the staff. I was a manager and an engineer on a drafting team for a log home company. And I ended up breaking the Novell network so many times because I wanted to learn how it worked, and then I'd have to go fix it, right? So my learning was like accidentally breaking the network and then learning how to fix it, and suddenly I became an IT engineer, and that's kind of been my role ever since. And I've done a lot of education, I've done a lot of engineering, management, all aspects of IT, specifically in data networking. So today I mainly do video training for Pluralsight. So I'm a freelancer and I create video content for training for Pluralsight. CCNA is my main focus there for getting people trained up so they get that entry-level certification. I also do Network Plus training there, as well as Wireshark. And our Wireshark library of courses at Pluralsight is expanding rapidly, right? As a matter of fact, is your course published, Chris? Woohoo! So Chris Greer's course just got published on Pluralsight, and both he and I are going to be doing more in the future on that. So you should expect to see that library of Wireshark courses there grow. At any rate, what we're here to talk about today is what every engineer should know about TLS, right? And this is listed as a 2-fin course. I would put it in between 1 and 2 because you have to know something about Wireshark and you have to know something about basic networking, how the protocols operate in order to get to this point. But really what I found, even in my own research and my own education about this, is that the information about how TLS works and what it is limited at best. Most of the information out there that I read, you have to have some really good understanding of how TLS works in order to understand what the author is talking about. So what I wanted to do in this is dispel some myths and get rid of some frameworks that are in a lot of your minds, because it was in my mind, about how TLS works so that you can actually understand how to do it, and it's going to make decrypting it a lot easier, right? So what every engineer should need to know here. What we're going to do, we're going to talk about a couple things here. First, we're going to do a brief history of this. I don't like to spend a lot of time on the history, but I think it adds some really good context. We're going to talk about the basics of encrypting data. We're going to spend seconds on that. And then we're going to talk about the key exchange process. The key exchange process, that is where engineers who know just enough to be dangerous about Wireshark and networking, that's what messes people up here, typically. There's a myth about that key exchange and about how encryption happens in SSL or TLS. We'll talk about some data encryption protocols. Then we're going to talk about the TLS 1.2 and 1.3 handshakes. There's a pretty big difference, and I would just want to introduce you to what the differences are. I think there's a couple other SSL presentations at SharkFest this time, which is fantastic, and I think they're at different levels of understanding. So here you're going to get the kind of the basics intro to it, what you need to know, and then Peter's doing a presentation, Peter Wu's doing a presentation, and then there's another engineer doing a presentation on SSL as well, I believe. So that should be great. And then we're also going to look at decrypting all of this in Wireshark. We're going to see what is it that we actually need to capture and how do we capture it, and what are the limitations of that. So my work you can find at pluralsight.com. After the presentation, I have some free trial cards. So if you want a 30-day trial, I have a bunch of them here. If I run out, you can just email me. I have pretty much an unlimited stack of these. I'm just out right now, so just need to get some more. All right, so let's start with the myth, right? In HTTPS, true or false, the public key encrypts the data, the private key decrypts it. It's false, but there wasn't a unified group of people shouting at me, false, Ross, no, it's false, right? It's like a couple spatterings of this. So the public key encrypts the data, the private key decrypts the data. This is describing what kind of encryption? Asymmetric, and specifically what protocol? This is RSA. Rivish, Shamir, Edelman, three really smart dudes in the 70s came up with a way of saying, hey, here is a public piece of information, use that to encrypt your data, send it over to me, I'll use my private key and I'll decrypt it, right? There's problems with that protocol, and there's a reason we don't use it, but this, in my experience, this idea is the source of a lot of problems that engineers have with SSL and understanding what's happening with it. So first off, web browser encryption. What's happening here? We have two components when we're talking about web browser encryption. One, we need a protocol that's going to negotiate an encrypted session between a client and a server. So that's first, right? Well, what do we use for that? We use either SSL or TLS. And since I've been teaching this session and doing work with this, I have heard all kinds of crazy things about why there's a difference between one and the other. Well, SSL is used for this thing, and TLS is used for this other thing. But they're definitely different. There's nothing the same about them. They're used for specific things. That's totally false. They're the same protocol, just the different name. I'll tell you why in a second. The second thing we have here is encryption protocols, right? So that the SSL or TLS is going to negotiate a session between the client and the server so that we can use one or more, at least two of these protocols we're going to use. RSA, Diffie-Hellman, or elliptical curve Diffie-Hellman. These are our asymmetric protocols. Then we have symmetric protocols, Triple DES, AES, and Cha-Cha-20. Right, so the idea here is that we're going to use both a combination of a symmetric and an asymmetric protocol to get our encryption done. Let's look at how this came to be. So, SSL first was introduced in 1994 by Netscape. Netscape was the first commercial browser out there. Netscape had a customer come to them and say, hey, we want encryption. We want to do e-commerce, we want encryption in the browser. So an engineer quickly, like within a couple days, wrote up SSL and implemented it. It ended up to be kind of garbage, easily reversed and decrypted without much effort, right? So it was only a year later that SSL version 3 came out. Now SSL version 3 is odd because it was only like a year and a half ago I was doing captures, just doing testing to learn about this stuff more, and I found servers on the public internet running SSL version 3. Right, which is, that's 1995, right? This is an old protocol. So we have 95, we have SSL v3 came out, right? By 99, what was happening 95 to 99? What was the big ordeal happening there? Browser wars. What does that mean? Well, yeah, well, Windows 95 came out in 95, right? And they installed Internet Explorer by default on all the computers, and you couldn't uninstall it, and it was forced as your primary browser, and Microsoft lost an antitrust lawsuit about it, right? So this is a big ordeal, right? So between 95 and 99, we have the name shift from SSL to TLS. And what happened is Netscape gave up control of that protocol and said, let's hand it over to the Internet Engineering Task Force, IETF, right, who maintains IP, TCP, all of that, handed it off to IETF and said, here, you guys maintain and keep the standard now. Well, who's at that table when they talked about what the standard would be? Well, Netscape was there. Microsoft was there. Do you think Microsoft would have it? Do you think Microsoft marketing would allow a Netscape branded name, SSL, to become the public protocol name? Absolutely not. So they changed the name to TLS. That's it, right? So now you have engineers calling it SSL and TLS. As a matter of fact, it's only been the last like couple versions of Wireshark where you could actually do a search for TLS instead of SSL. But they're the same thing. There's no difference. It's just a different name for the protocol and the version number. So time passed here, really these updates to the protocol are enhancements because of security issues all the way up until TLS version 1.2, right? The protocol generally operated very similarly, generally speaking, pretty similarly up until 1.2. Once we get to 1.2, the jump to 1.3, that's when it gets a little awkward. So 1.2 came out in 2008, wasn't really even implemented till 2013, at least support for it on the client side, on most clients. And then it kind of took off. We're starting to use 1.2 more, and now we have access to TLS 1.3, which is a proposed standard via the IETF. So really, in today's world, if you are running a web server that's encrypted, we should be either using TLS 1.2 or 1.3, nothing less. Right, and it starts to get even deeper than that. We're starting to find out that there's holes in all these protocols. So one of the big issues with, getting ahead of myself, we'll come back to that. Data encryption basics, we'll get here. So here we're going to look at, symmetric versus asymmetric protocols. But I'm not going to talk about it like that. We're just going to talk basic here, right? So when I want to encrypt some data, all I do is I take my message, I run it through an encryption algorithm. And I run it through the encryption algorithm plus some key. And when I do that, that spits out mathematically an encrypted message that I can then send across a public channel, and no one in the middle theoretically can read that message. The server then can take that same message, run it through the same algorithm with the same key, and come up with the original unencrypted message. Right? The problem here, though, is if I need the same key on both sides, how do I get both sides to have the same key without the person in the middle knowing about it? Right? So I cannot send that key over the public channel, right? Or everybody could decrypt that data. So we're not going to send that key over the public channel. We need some method of doing that, and that's our key exchange protocol. So the key exchange protocol here, the whole intention is to take a key that the client is using and tell the server about it and have no one in the middle know about it, right? And this is where we get asymmetric encryption, right? The first one was symmetric encryption. Both sides are using the same key. It's a symmetrical key, that both keys are the same. Here we need a way of sending the key without anybody knowing about it, so we're going to use an asymmetric process. So I'm going to quickly go through how the Diffie-Hellman key exchange works. This is a lot of math, but I try to keep it really simple because I think the math is pretty nifty and pretty simple, actually, right? There's not a lot of work here. There's only one operator that's not common to most people. So the way our key exchange works with Diffie-Hellman is we take two numbers here, and the two numbers are P and G, and they're contained within the certificate, right? They're contained within that certificate. So they send P and G over to the client through the process. So in the process of our TLS handshake, the certificate gets sent to the client. The client can then yank out the P and the G values, and they can use that then to start the asymmetric process here of Diffie-Hellman. Anyone can know about that public key, right? What will happen next is the client is going to pick a private key, all right? The key is going to be much larger than these single values that I'm using here, of course. I'm using the simple values just to make this easy for humans. So we pick a private key and we run it through a formula. All right? The formula here is we take the G value, 17, we raise it to the power of A, which is 8, and then we do a modulus P, which is 149 here. Well, what the heck's a modulus? If you're like me, we never did modulus math. I studied engineering. We didn't have to do that in structural engineering, right? So the modulus, you remember this from third grade, right? If we have 95 divided by 8, we go through the process, right? We get 8 goes into 95 11 times with some more left over, right? 11 point something times. Well, we don't care about much else in this process except for that remainder. So in modulus math, all we care about is What's the remainder from that problem? All right, so that's it, right? We don't know, most of us don't use this daily, but that's a simple problem. So what we do then is we run that through there, we get 17 to the power of 8, mod 149, we get 5. Right, I'm calling this the encrypted session key here. It's only a piece of the session key. So this 5 becomes another piece of public information now that we send over to the server. Right, so we send this number 5 over to the server. Server is going to do the same exact process. It's going to pick a private key. We're going to run it through the same formula, G to the power of B mod P. And that's going to give us our key here, our encrypted key of 16. We send that over to the client. We run these numbers now through the formula one more time. This time what we do is we take the encrypted key value, we raise it to the power of our private key, mod P. On the server side, we take the encrypted key we got from the client, raise it to the power of B, our private key, mod P again. What this results in then is the same exact number on both sides. All right, so we get 129 on both sides. That's our session key. Right, all this math you can do in Google, like just you type it into Google and it'll pop out the numbers for you. It's pretty simple math, right? There's not a whole lot going on here. We're just not using Diffie-Hellman a lot anymore in our key exchange. All right, and the reason is we're not using Diffie-Hellman, not in this form, is because the way it's implemented. It's not necessarily insecure, it's just that the way it gets implemented on web servers can have it so that attackers can have an easy time of forcing small key sizes so they can reverse engineer the key. So we try to avoid using this Diffie-Hellman process now. However, it's real similar to how the next one works. So this is pretty cool math, I think. All right. So we have the key exchange process here. It works a little differently in TLS version 1.2 versus 1.3. All right. So in TLS 1.2, we can use RSA to do our key exchange. Right? That's public key encrypts, private key decrypts. We can do that here. We can use Diffie-Hellman, or we can use elliptical curve Diffie-Hellman to do our key exchange. But we don't use RSA anymore. There's too many issues with it. It cannot provide perfect forward secrecy, meaning that we could technically capture an encrypted message, and then later on, if we got access to the private key from the server, we could decrypt it. Right? And we don't want that to happen. So RSA is kind of out. We should avoid using RSA. Diffie-Hellman is also out. We should avoid using Diffie-Hellman because Diffie-Hellman, the way it's implemented, is a problem, which leaves us with elliptical curve Diffie-Hellman for TLS 1.2 that is advised to be used. We can use RSA, we can use Diffie-Hellman, but the elliptical curve is the one we want to use. In TLS 1.3, that's the only option we get. Right, that's the only option we get is to use the elliptical curve. And we'll see the reason for that. It allows the handshake to be really, really efficient. And it allows us to encrypt our data sooner than later. So elliptical curve, we'll go through this briefly. Elliptical curve works real similarly to how we saw the other math work. What we're doing here, though, is we're picking this curve type. So mathematicians came up with a series of curves that work well for this type of encryption. And you're typically going to find one of the top two curves being used, either X25519 or the SECP 256R1. So those are the curve types, and it's just a shape of an elliptical curve on a graph. When we use this for Diffie-Hellman, what we're going to do is we're going to select some points on this curve. And the points that we select plus the curve, that's going to become our public key. Right? So our public key here is going to be this curve. What we'll do then is we'll pick a private key on the client side. We're going to mathematically combine it with the curve, and that's going to pop out that encrypted key value. When we're using Diffie-Hellman elliptical curve in TLS 1.3, what's going to happen is that the public key, the curve type and those points, and this encrypted information, right, our encrypted session key, that's going to get sent over all in one transaction. We're going to pick the curve, pick the points, pick our encrypted key, do the calc, send it over. Server is going to do the same thing. It's going to take that encrypted key, hold on to it. It's going to do the own calculation with the curve type plus those points. It's going to generate its own encrypted key. It's going to combine that and tell it, say, yep, we're using this curve and these points. Here's the key. And now we can do the math in reverse. We combine the private keys with the encrypted keys on both sides, and we get the same session key on both sides. Right? So it's doing the same basic formulation that we saw with standard Diffie-Hellman. Here we're just doing it with the curve. It makes a more efficient calculation. We can get a stronger key with less computation. This process is computationally intensive, which is why we don't use it for our bulk encryption of data. Right? It's why we're getting this key. We're getting one key, one piece of data transferred. Then we can use that one piece of data, that key, to do a symmetric encryption, which makes it much faster, right? Which is the next component here, right? So if we look at our data encryption, we're going to use some symmetric key protocols. We're going to use that first process. We're going to use Diffie-Hellman elliptical curve to get the same key. Then we're going to use something like triple DES, AES, or Cha-Cha-20 to do our encryption. And I was a bit premature with my slide there. We're not going to use triple DES. It's old, right? AES replaced it 2 decades ago, or maybe not quite 2 decades now, but AES has been around for a while. So AES or Cha-Cha are the preferred methods here. So we should not be using triple DES anymore. So we have our key exchange to get our session key. Then we're going to do our bulk encryption with either AES or Cha-Cha-20. There's other components to this as well. You see I have GCM and CBC there. These are for these are Galway counter mode and counter block. Why can't I think of the name? Cipher block chaining. Thank you. These are for validating our encryption, right? So I'm not going to get into that in this presentation. All right, so the other component here of TLS in this negotiation is some handshake integrity. We want to make sure no one tampers with our handshake. So we take a little piece of every component of the handshake and we put it into the last message in our final message on both the client and the server side, and then we use some type of hash like SHA-256 or SHA-384 to create a hash of that so that we can verify that no one has tampered with our handshake in the process and potentially compromised our keys. The only thing that's left here is, what does the certificate do? Right? As a certificate being, if we're using Diffie-Hellman elliptical curve, did I talk about at all what the certificate is used for? No, it's not used. So we're not using the certificate when we're doing Diffie-Hellman elliptical curve. Why is this important? Well, if you read blog posts about how to decrypt traffic in Wireshark, a lot of them will tell you to get the private certificate key from the server and put it into your Wireshark, and then boom, it'll decrypt the traffic. And then it doesn't work. Well, why doesn't it work? Because we're not using which protocol for our key exchange? RSA. We're not using RSA. Should we be using RSA? No. In TLS 1.3, can we use it? Nope. So the certificate, what's the certificate doing? It's just validating that the server says who it says it is. We're not using the certificate to actually do the encryption anymore, right? Unless we're doing RSA. If we're doing Diffie-Hellman, there's a couple values in there. The P and G values are contained in the cert. But otherwise, really, we're just using the certificates to validate that the server is who it says it is at this point, right? Our certificate is not used for the encryption anymore. It's much more secure to use Diffie-Hellman elliptical curve. So, how then do we get our session keys to work? Well, there's been some new hiccups in how this process works. There's always hiccups in how this process works. You guys have any questions so far? Yeah.
Is adding that curve to the elliptical curve Diffie-Hellman, is that like salting? Like adding another random value?
I don't think so, but I'm not a programmer either, so. it's a different way to grab, it's a different way to generate numbers instead of using large, we still, yeah. Anything I say about it, I'm going to be talking out of turn. So, anything else? All right, so we can do this. I'll do this demonstration in both Windows and Mac. Do you have any Mac? Yeah, you got a bunch of Mac users. All right. So we used to be able to use Firefox to do this. As of a couple weeks ago, a couple months ago, Firefox said, no, we're done. They wanted a more secure browser, so they turned off, by default, they turned off the ability to actually capture your session key. So you can't use Firefox anymore, at least today. That could change, but you cannot use Firefox today to capture your session keys. All right, they wanted a more secure browser, so that's how it goes. And I understand, right? I could, when you see how easy this is, I could see writing a virus to go like capture session keys and send them out. Okay, so on our Windows machine, what we have to do is we have to set an environment variable and tell it to export SSL keys when possible. So the way we do that is we go to Control Panel, and in Control Panel we go to System, Advanced System Settings. All right, Control Panel, System, Advanced System Settings. Then we go to Environment Variables. And up on the top, get Sharky going here.
You did not bring that. Did you bring that?
I did. I put a laser on it. I put a friggin' laser on my shark head pointer.
Wow.
Look at that. So up here, up here we have the SSL Key Log File. I added that, all right? And that's the one we need to add. Yeah.
Any difference whether you add it as a user variable or a system variable?
I believe it needs to be a user variable. So you just type in SSL Key Log File in all caps, and then you give it a place to put it. Right? You have to tell it a place to put it and a file name. So here I just called mine, in my documents folder, I called it sslkeylog.log. Hit OK, 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 OK. And now, if I open up my documents folder, right now I have no SSL key log file in there. Let's start up Wireshark. Start a capture. And then I can open up Chrome. And once Google pops up there, if I go back here, I already have SSL key log files already been populated there. All right, so once I start it up, it already starts populating the keys into that file, and you can actually open it up and see. Oops. You can actually open it up and see all the keys that it's keeping. Right, these keys there's a lot of them. They change a lot. So it keeps a list of all these keys. If I go to Control-Shift-N, SharkFest.org. Oh, I went to Wireshark earlier. Too many R's. Okay, great. Stop that, close that, stop my capture. So if I look here now, if I do frame contains Wireshark, it should pull up one of the TLS hellos, right? Because in the TLS hello message, it puts the server name. So frame contains here will isolate that for me. At least it'll get me to the point where the message that I need is. And then there's all kinds of ways to do this part. I can follow the SSL stream, or I can apply as a conversation filter for TCP, and then that'll show me my TCP data here. So here with Wireshark.org, we're using TLS 1.3. All right, so we have our client hello. Inside the client hello, I have a bunch of information, including the server name. Right after that, we see the server hello. And in TLS 1.3, there's no more handshake after that. Let me come back to that in a second. So I have my session key. I have my capture. Now to get that in there, all I do is there's lots of ways to get into the preferences, but easiest one here, right-click on transport layer security down here in my packet details window, and then I do protocol preferences and open TLS preferences. And what I'm after here is this pre-master secret log file name, right? I'm not going to bother with the RSA keys list because I'm not using RSA. So we browse, find my documents folder, Ssl Key Log, open and OK, and instantly we get decrypted messages. Yeah?
Why is it called that? Why is it free? What's master when those scores are new?
I don't know. Yeah, go ahead, Peter. Fancier math, right? You're right. This is the introduction side of this. So, all right. So now we get more information too with our handshake information. So now we have our decrypted data. We can see that this is HTTP2 traffic, right? And there's HTTP2 conversations happening there. So let's talk about these handshakes then and what's happening, right? We know how to decrypt the traffic now. We know how to capture the session keys and decrypt it. We'll do this on Mac quickly, and I can show you the same thing on the Mac. This will also work on Linux. If you have Linux or Mac, this process will work. So on the Mac or on Linux, we're going to open up a command prompt. We have to tell it to export our Ssl Key Log File here. So we use the word export. Ssl Key Log File equal to, and then a location. So I'm going to grab this location. So I'm just going to put it in my documents folder under the Ssl key folder. I'm going to call it Ssl Key Log File .log. Let me hit enter. All right, now it's just going to instruct the workstation now to export this key. Next, we're going to launch Chrome. Open-A Chrome. Oh, can't do it that way. There we go. So once we launch Chrome here, our Ssl key log file should populate here. There it is. So now I have my Ssl key log file on the Mac. Same exact process. Right? From this point forward, it's the same process. Can't use Firefox. Right? This will work with Chrome. Yeah. Correct. Yep. And you have to launch Chrome in this way. You can't go click on it. It has to be launched from this terminal window for it to grab that information about that variable.
You put that in your batch history?
Yeah. Yep.
Got a question for you. The SSL log file, will it sit there and keep expanding even if you go into the same website over and over again, or will it already know it?
Yeah, because those keys are going to change depending upon if it's going to reuse a session or not, right? So TLS has an option of reusing a session, but it's not always going to do that. So, and then once that's different, it's going to change the key, or after time, it's going to change the keys. So yeah, you're going to always need new keys.
So it's just going to keep adding to the bottom of the file,
Mhm.
then it's just going to keep growing and growing and growing.
Yep.
Okay.
Yeah.
So capturing browsers in a sandbox environment is fine, but what about capturing arbitrary third-party applications?
Arbitrary third-party applications, right. This is a problem, right? You have an app on your phone, and you're trying to do some troubleshooting, and you want to decrypt the traffic, or even app on your machine. Yeah, that is an issue. You either have to, the developer either has to build that into their code to export that, or you're going to have to do a man-in-the-middle attack on it, right? And a legitimate one, right? So use something like Ssl Split, which is, data loss prevention devices use this all the time. In fact, the Squid proxy has this built into it now, where you can send traffic through it, and it'll decrypt your traffic, and you can grab the session keys out of that, right? Because you're just setting up two separate SSL sessions, and then you know the keys for one of them, so you use that to your advantage.
Does it say open-a application was the rest of that line?
That's the Chrome application. Yep.
So that has to be done in the same terminal window?
Same terminal window, yep. Yep, has to be in the same terminal window. Was there another question over here? Yeah.
So that works on Linux, it works on Chrome, works on Internet Explorer?
Nope. Not no Internet Explorer, no Safari, Chrome. You get Chrome right now. Yeah, I would be unsurprised if Chrome takes away this feature in the future as well. So, and at that point, we're stuck with man-in-the-middle attacks, right, where you have to set up something more sophisticated to do it. Cool. Were there other questions about this? Yeah.
So, just a question, if you work for a large corporate company or the hotel or whatever, and you log in by this method, are they doing authentication in the middle to verify that you're not?
Nope.
Or
Is anybody checking to see that you are or are not capturing this?
no, in the sense that, are they forcing authentication with them? They would only have one key in between you and the...
No, this is the key, right? Because the two parties that have the key are your workstation and the server. The endpoints have the key, and those are legitimate authorized users of the key from the application standpoint, right? Those devices have to have it, so there's no need to verify in the middle that those keys are authentic, right? Because the two parties agreed on them. The challenge becomes if you're a man in the middle looking at that data and you get the key, that's a special thing, right? You have to do an attack to get that key, right?
Can you show the Windows one?
Yeah, no problem. No problem. Yeah, so in Windows, we go to Control Panel. We go to System. Advanced System Settings. Environment Variables. And then you're adding in the Ssl Key Log File. So what you do is you type in all caps Ssl Key Log File, and then you give it a place to put it. So let's put it put it on the desktop this time. And then you have to give it a file name. The file name is not important. You can call it whatever you want. All right, any other questions? Has this been helpful so far? All right. Let's go look at some handshakes. Yeah, go for it.
What if you're on the opposite side and you're capturing from, say, the server?
On the server side, I am that's beyond my scope. I'm certain there's ways to grab it on the server side as well, especially if it's a HTTPS server, you know, running on like Linux. I'm sure there's ways that you can grab that. I just don't have the methodology for that. I'm sure if you talk to the developers, they could probably lead you in the right direction on that one. So, anything else? All right. So I created a OneNote page so that you guys can have access to some of the links and some of the files that I'm looking at. I wrote the URL up here. It's also written up on right in the notebook itself, so you can get to it that way. So I have my contact information in there, link to my training at Pluralsight, and then the real important stuff here is at the bottom. There are two links here that an engineer developed, and they're super impressive, and that's this TLS Illustrated. And what he did, this is...
Yeah, let's go. Well, it's in the OneNote.
in OneNote.
Go to the URL. It'll all be there in the OneNote.
Yep, right on. This is why I did this. Betty, you're brilliant.
The developer did this. It's super awesome.
Super awesome. Moving on.
Step by step.
Yep. So what he did is he outlined the process and he annotated it down to the bits. So you click on client hello, right? You click on client hello and it says, okay, this is setting the protocol version, some random client data, blah, 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 blah. Right? We click on annotations and he explains all of it
Oh, that's just accurate.
in wicked detail. Right? I would love to go through this all today, but that would it took me 2 weeks to get through these. Like do a capture side by side and like walk through bit by bit. Took weeks. Yeah.
Is the developer here, this is absolutely the very best.
Isn't this awesome?
I've been doing this for 20 years, this is very, he's missing cha-cha, unfortunately.
Well, he set this up saying, in this demonstration, the client connects to a server, right, doing a ping and a pong, right? So it's something real simple, right? He just needed a baseline to use it. Isn't it great? Yeah, I hadn't either, and I've been really enjoying this, right? We could probably sit and go through these one by one, but I mean, that'd be a snoozer, right? I mean, I already saw people falling asleep when I was talking about the math, and I know it's warm in here, and you know, all that, and I'm, you know, we have a super exciting topic about math and encryption, but yeah, this is great. So what we're looking at here is with TLS 1.2. The basic process here is that the client sends a TLS hello message. So we have three-way handshake, sin, sin, ac. Then the client sends a hello message, right? And in that hello message, the client is going to specify what cipher suites it supports, and it's going to send some other information in there, all right? So it's going to say, hey, I'm the client, and I support all of these cipher suites, right? So here it's, you know, we can have the top one there is TLS ECDHE, elliptical curve Diffie-Hellman ephemeral, with RSA, with Cha-Cha 20, and Poly 1305, SHA-256. Right, so we're saying we're going to use elliptical curve Diffie-Hellman for the key exchange, Cha-Cha 20 for our bulk encryption, and SHA-256 for the handshake integrity. All right, so the client gets to say what it supports. After the client sends the hello message, the server is going to reply with a server hello. The server hello is going to say, okay, we're going to pick this cipher suite. So the top one there, the server says, okay, I looked at the list. This is the cipher suite that I want to use. You support it as well. Here it picked elliptical curve Diffie-Hellman. With RSA, with Cha-Cha 20, and Poly 1305, SHA-256. Right, so we're saying we're going to use elliptical curve Diffie-Hellman for the key exchange, Cha-Cha 20 for our bulk encryption, and SHA-256 for the handshake integrity. All right, so the client gets to say what it supports. After the client sends the hello message, the server is going to reply with a server hello. The server hello is going to say, okay, we're going to pick this cipher suite that I want to use. You support it as well. Here it picked elliptical curve Diffie-Hellman excuse me. It picked elliptical curve Diffie-Hellman with AES encryption and SHA as our handshake integrity. All right, so the server just chose this based on what was available on the server side. So now we know what version we're using. Now the server is going to send over its certificate. The server is going to use elliptical curve Diffie-Hellman, so it's going to pick the curve type, the points on the curve, and it's going to generate that encrypted value that it can send over to the client, right? So the server then sends that key exchange information over, says, here you go, here's my key information, you're up, client. The client then does its key generation, right? Client takes the elliptical curve that it got from the server, plus the public points, combines it with its own private key, generates a number, right? And now the client sends that back to the server. That's the client key exchange piece here. Client sends it back to the server. Now the server and the client both have all the information they need to do their key calculation. They do their key calculation, and then they start to finish up the transaction. Let's look at this happening. So, this is pre-decrypted. I'll decrypt it in a second here. So we have our three-way handshake, SYN, SYNAC, ACK. Next message, the client at the 10 dot address, 10, 128, 50, 148, is going to send a message now to the server. Here's our client hello. If we go look at the details of this, should I make the text a little bigger? So if we open up TLS here, we can see some of the records that have been changed. Here's the client hello. What am I looking for here? There we go, cipher suites. So here's the client saying, these are the cipher suites I support. What's missing from that list of cipher suites? Diffie-Hellman. What does that mean? I'm using Firefox here. This is Firefox from a year ago or more. What does that mean about Firefox? Firefox is saying, I don't want to use Diffie-Hellman anymore. Right? So Firefox won't even allow a server to communicate with it on Diffie-Hellman unless you modify Firefox. Right? You can modify Firefox to say, connect with any protocol I want. It left in, this is a year ago now, it did leave in RSA for the key exchange. Right? But why do you think that is? Well, if you're a developer and your web server is sitting on the same computer that you're working on and you're trying to do some decryption, I can guarantee you, you're a developer, you're going to force everything to use RSA, so you can grab that private key file from your server and throw it into Wireshark, and then you don't have to grab these session keys all the time. You can just use the private key to decrypt the data in Wireshark. But you can't deploy an application like that. Right? You shouldn't deploy an application like that. So there's our cipher suites. If we look then, our server hello then is going to come back and it's going to tell us which one we picked. So here it's picking TLS, it's going to say elliptical curve, AES 128, SHA 256. Next, the server sends its certificate, sends a bunch of information here. We have the server key exchange information. So here's our elliptical curve Diffie-Hellman parameters, right? So we have public key information, right? This value here is effectively, this is our curve type, the points on the curve, plus our encrypted information that we're going to use to generate our key. And right above it, we can say that it's the SECP 256R1 curve. The client then does the same thing, right? The client sends back the information, including now an encrypted message. So here's our Diffie-Hellman parameters that it sent, and everything after this now is encrypted. So now we see encrypted handshake message, because now both the client and the server have all the information they need to calculate the keys. So now they're going to start encrypting data. So everything after this, we're not going to be able to look at. Right? We have this cipher change spec message, but we can't see what's in it because it's encrypted. Right? And really, this is the server is finishing up. The server and the client are finishing up the conversation. But if we decrypt this, right, the client key exchange, and then we have this next message here. The client key exchange, remember, a piece of that was encrypted? Well, now it's not, and that encrypted piece of the message just says finished, right? And our handshake integrity data is in here, our verify data. So this is our handshake integrity now from the client side. And then the next message here, change cipher spec finished with the verify data. This is the server saying the handshake is done. Here's the information you can use to validate it. Right? So we say, it's the client says, this is what I support. Server says, we'll use this one. Server sends it some certificate information, some public key information for the key exchange. Client sends back the information. We start to encrypt the data. Then we can have our conversation. This one is old enough where it's actually, I have HTTP data in it yet, so you can actually follow my HTTP stream and you can see the website that I collected. HTTP 2, you can't do this anymore. Not like this, at least. All right, so that's TLS 1.2. TLS 1.3 is pretty nifty because it speeds up this process. Let's take a look at what it does. You guys have any questions about this? Okay. So for TLS 1.3, we do something pretty nifty. What key exchange protocol are we going to use? Do we need, let me ask it differently. With TLS 1.3, do we need to negotiate which key exchange we use? No. So, because of that, with TLS 1.3, we just start off by saying, I think the server is going to be able to support the elliptical curve that I choose with my public points. I'm going to assume that the server is going to support that. So the client just says, the client generates its key information, which means it picks the curve, picks the points on the curve, and generates that special encrypted key with its private key. And it sends that in the client hello right to the server. Server comes back and it says, all right, here's my key. Boom, everything is encrypted after that. So now when the server sends it's a message saying, yeah, this is it. We're using this encryption now. Let's go. From that moment forward, in TLS 1.3, everything's encrypted. So when the certificate is sent now, the certificate is sent encrypted over the public network, which is a really good thing. It means that somebody cannot tamper with the certificate while it's in transit, right? So here now we have our certificate encrypted in our message right in the handshake. The handshake becomes encrypted much sooner, which is one of the values. And we didn't have to negotiate between the client and the server about what protocols we were using. We just assumed, the client assumed and said, boom, let's go. Let's start encrypting. Let's look at, this is better to look at in a capture. So here we go, three-way handshake. The first message here, it says, it's listed as TLS 1.3, client hello. Let's open up our TLS preferences here and see what's going on. So TLS 1.3, what's this? It's just a handshake. TLS 1.0 though, right? This value is kind of fixed now. The value, this TLS value we see in our hello message to describe, well, in our handshake message that contains the hello message. In this message, it's saying it's TLS version 1.0. And it's doing that because the client does not know what version of TLS it supports, right? The client has no idea at this point if the server is running SSL version 3 or if it's running TLS 1.3. Client has zero clue about it, right? So the new protocol specification says, leave this set to 1.0 so that the server, regardless of what protocol it's running, it'll accept the message. If we look in the client hello message now, this makes TLS super easy. Hello message says, hey, we're going to use TLS 1.2. Nope, that's also not true. This is a trick, right? This is a trick because of middleware boxes, right? I'm guessing if you're working in a company that has more than 500 employees, you're probably using data loss prevention equipment, right? Do you guys know what this is? All right. If you don't know what data loss prevention is, it's a man-in-the-middle attack that your corporation does so they can decrypt, inspect all the data that comes in and out of the internet connection, right? If you force that to be TLS 1.3, a lot of those middleware boxes break. So imagine, you implement a new server and you're trying to do inspections of all that data to see if anybody's stealing your stuff, and the minute TLS 1.3 comes through, it breaks. So you either can't decrypt the data or the customers can't view the website. So we trick it. We just say this here. So then if we look next here, there's a bunch of information in here, including the cipher suites supported, right? Because we do need some of that. We need to know which symmetric key encryption protocol to use. But if we scroll down here, now in every browser, regardless of which version of TLS that will be used for the conversation, we're going to send our key share information right away. So, in our client hello, regardless if we're using TLS 1.1, 1.2, 1.3, the browser is going to send the key exchange information in case the server supports TLS 1.3. Right? So it's always sent, regardless of the server version. The client is just like, I don't know what you're going to use. Here's everything that I can do. If we can do TLS 1.3, we're going to use this key exchange information. There's our public curve type, 2519, and then the key exchange information. All right, points on the curve plus the encrypted message, or the encrypted key. After we send that client hello, the server comes back and it says, yep, we're good, right? The server says, here's a cipher suite we're using, AES SHA-256. We don't even say that we're using elliptical curve anymore because it's assumed it's TLS 1.3. That's our only choice. Key share information, we got our group type, we got our key exchange. Right? So the server's sending the same information back to us. And then after that, it says change cipher spec, and then everything after that is encrypted. So we're still in the handshake. The handshake is not yet completed, but we cannot see the handshake anymore because it's now encrypted. Let's decrypt that. So now we can see that the server sends this message, but now we can see what's in it, right? And it's just some more information for TLS to negotiate. Then we can see the server sends a certificate, right? And we can see this now because it's decrypted. Once the server sends a certificate, the client can come back and say, yeah, we're done. This process is a lot shorter, right? It's a lot shorter because the client hello says, here's my key exchange information. The server says, great, here's mine. We're encrypted now. Server says, here's a certificate. You can validate my authenticity. I'm finished. Client says, I'm finished. Let's start our real conversation. Right? So it happens a lot faster, and more of the message is encrypted. And you know, this may save only a couple milliseconds of processing time, maybe even 20 milliseconds of processing time, but that's a big deal over time, right? And just the quantity of messages we're talking about, to reduce the number of messages in the handshake by a few messages is a big deal as well. So TLS 1.3 here, just the whole process is much, much, much shorter. All right, I've been yakking away for an hour now. The temperature has gone up steadily in here. I'm sure no one's noticed. Let's open it up for any kind of questions you have that I can hopefully answer about this. Did you guys learn something today, first of all? Right. Yeah.
So if the direction of encryption protocols is moving towards more difficulty to decrypt in a troubleshooting scenario, it would almost be that if you have a problem, you actually have to move into a lab setting where you have the facilities to do it. Is that where it's going?
Yep. Yeah. So the question was, you know, as the encryption becomes a little more sophisticated, it's going to become harder and harder to get the decryption information to actually decrypt these messages, which means that, yeah, you're oftentimes going to be forced into a lab environment, or you're going to be forced to use hardware like a man-in-the-middle attack, like SSL proxy, where, you know, you're actually, when I say SSL proxy, man-in-the-middle, is anybody brave enough to say that I have no idea what the hell I'm talking about? Okay, all right. Let's see how this magic works. Oh, look at that. And then you get to look at it later. So traditionally, we have a PC hooked up to some network connecting to a server, right? So when we're doing this method, we're capturing the keys either on the client or on the server, and this is completely legit because both ends are authorized to have those keys. They're the ones having the conversation with each other. But if I'm in the middle here, if I'm this guy here, and I want to see that conversation, I need a way to get at it. So this computer here could be a data loss prevention device, right? So, you know, you work at a bank, and you stumble upon one day that somebody leaves themselves logged into your computer, and you discover that you can collect a whole bunch of account numbers from a whole bunch of customers. So you collect all those account numbers and their social security numbers and their addresses, and then you send it yourself an email to your personal email account, right? That's all encrypted, so it's going to be good. Well, at those companies, this data loss prevention device is going to inspect that. So the way that works is, instead of building the SSL connection or the TLS connection between the client and the server, we build two. We build one connection between the client and the data loss prevention device. This would be our proxy or our man in the middle. And then we build a separate connection between the proxy and the server. And now all the data in the middle here is decrypted. And because we own this proxy, this man-in-the-middle proxy, we also know the keys, so we can decrypt. Does that help some? All right, yeah.
So isn't the certificate in place in the concept to take care of that?
Oh yeah. You can't just be any bozo and do this, right? You have to own these devices or have administrative access to them to put a root certificate on it to say that this bogus cert is trusted. Because this thing is just going to put a bogus cert, right, on everything. It's just going to rewrite the cert and be like, yeah, here's a junk one. That guy should reject it until you tell it to accept it. So I'll get to you.
So I guess is my question I had earlier. So basically when you're doing your SSL key capture that you showed us earlier, that's never gonna change if the corporation owns that box and it's doing all the authentication.
Right. Right. Yeah. Yeah.
Yeah, so, some vendors like Apple will use certificate pinning, to prevent them from man-in-the-middle resign. Can you speak to that at all?
I cannot. There's ways around it, but that's beyond my skill level. Yeah.
Yeah, to elaborate on that, there's a few vendors that you're gonna start seeing because of this issue that will actually provide services to extract the keys at the client side.
Yep. Yeah, right. No, I'm expecting this to happen, right? Yeah, because you're going to need to this guy's point, whoever asked the question earlier about, this is going to get harder and harder to do. Yeah, we're going to need new software to do it, yeah.
Cert pinning is not there anymore anyway because of these kind of things.
Okay, so you're saying certificate pinning isn't in favor anymore, so, yeah, all right. Yeah.
Just looking at this from an application developer standpoint, let's say I own the client and I own the server, and I just want to be able to monitor traffic between them. So I already own the certificate that the server is using, but I just use that same certificate in the proxy, and that would be fine.
No. And there's a reason for it, and I don't remember why. Because you need. I'll give you an answer of maybe. How about an answer of maybe? Yeah, I can repeat the question. Sorry. You mean you can't hear what's in my mind? The question was, if you own the application, can you install the certificate right on your man-in-the-middle box?
Not just the application, but if you also own the server that you're
Yeah, if you own the server, and if you own the server, the application, if you own all the pieces of equipment from server, your proxy, and the client, can you take your server information and install it on your proxy box and have it work?
you would need the DNS to resolve to the proxy box.
Right, there has to be some messiness involved there. You'd have to have the private key on there as well. I'm not sure how that would work. I messed around with this for a long time. The secret is you need the private key from the server's certificate to do that. And I don't know how that would look if you put it in two spots at the same time.
And you would also need the DNS for the client to resolve to the proxy, and on the proxy, the DNS to resolve to the server.
And if you have all this information, why would you use a proxy? Other than to troubleshoot?
There are reasons.
Okay, yeah, I understand, so, yeah.
Maybe for a future SharkFest, you get the NSA to come in and tell us how they do it.
Well, they do it because okay, so this is a total rumor, right? But they did it because they had an informant on the committee that developed the AES standard. All right, so AES was a competition to develop the next generation encryption. So the theory goes, right, or the rumor goes, is that the NSA had an informant on the committee that wrote AES, and they have backdoors. Yeah, that's the.
The SNI field, which my organization uses to filter kids and stop people, is that going to be encrypted? Is it a requirement to be
No, because that's in the hello message.
encrypted? 1.3?
And, yeah, it's in the hello message.
And it's still going to be encrypted?
It can't be unencrypted. The SNI? It doesn't? Okay. Right. Yeah, my skill level is more on networking and analysis than it is on the server side of this, so, yeah. The question was, so I'll keep repeating the questions. Thank you for reminding me. The question was, will the SNI field be encrypted? And I just learned TLS 1.3 does not even use that field, so. Yeah.
You might want to mention one of the downsides of TLS 1.3, which is part of why it's still only proposed. The keys are ephemeral. If you're a bank or other financial institution, you're required by law to say
All right. Unless you save the keys, right? Well, they are, yeah, right. There's other issues with TLS 1.3 as well, especially in the session resumption. There's a way that the handshake can be unencrypted, or it can be decrypted easily as well, so, yeah. Anything else? Yes?
Even if you save all those keys, you're gonna be saving a session key for every, are they gonna be timestamped or IP you're gonna receive?
Well,
TCPs? I mean, that's a lot, you're gonna have to go through millions. I mean, to find the specific 5 microsecond session key that you need to encrypt or decrypt.
yep.
So that's like, that becomes like, you know, you're managing as much data to decrypt as you are managing.
Yeah, and you know, honestly, now that I think about that, that's not entirely true. If you're using DLP, and a bank is guaranteed going to be using it, you can log some of that data unencrypted, but it's still unencrypted now. You'd have to do some magic. I don't know how that would work. It's a problem for another engineer to solve, I guess.
Some ciphers disallow use of this technique, like with perfect forward secrecy, is it still possible to decrypt the session if you have the session?
If you have the session key, yes.
Okay, just man in the middle that PFS prevents, or?
The PFS prevents, what PFS is preventing is if I do a capture today on some server, and let's say it's using RSA, all right? Do a capture today, and then I save it, and 10 years later, I accidentally find that server in the garbage. And I go recover the RSA private key from it, now I can decrypt that, right? So it's preventing saving up those messages and then later on discovering the key and then using it.
So all the elliptic curve and cha-cha cipher, there's all PFS?
I do not know if they're mathematically proven to be PFS. Peter, can you answer that question? Is elliptical curve Diffie-Hellman proven to be perfect forward secrecy? Or is it just assumed? Okay. So yes. Okay.
You mentioned that you had this cipher that with ECDHA and RSA. ECDHA integrity is similar to DHA.
Say that again?
So, remember you had this like a picture of like hello with ECDHA ciphers and RSA.
Yep.
ECDHA is basically the same as the DHA.
Okay.
So, it's all for 40%.
Okay. Okay. Or even the RSA is because of the way it's. Are you saying the RSA is too, or just the DH? Yeah, only the DH. So to answer your question back there, the answer is yes. Yes, it is perfect forward secrecy guaranteed.
Only for the DH, the cha-cha is symmetric.
Cha-cha is symmetric, yeah, that's right. Cha-cha is symmetric, yeah, that doesn't apply there. Yeah.
So, given the fact that you said that Firefox doesn't fork anymore, neither does Safari, but Safari's based on Chrome, right? Ish, sort of.
I think they had a departure a couple years ago.
Okay. Do you know if there's any other tools aside from a browser that you can use to be able to generate this? Some kind of like command line tool or any other tool that?
No, it has to be, so to get the session key, the way that I understand the browser is working, like in Firefox, is there is code in there written specifically to export those keys, right? And it's still in Firefox, it's just off. The compiled version for the nightly builds are off right now. So the way I understand it is you need this code snippet in the application itself in order to be able to chuck those keys out. So any application I would expect could have this functionality built into it. I think if I were an app developer, I would never put this functionality into it, right? Because I wouldn't feel strong enough to be able to prevent my nerdy white hats and black hats from being able to take advantage of that key export, right? So that's now you're in man-in-the-middle territory, right? So I think that's, a lot of that, or the software that the gentleman in back was talking about too, that would allow you to do this right on your workstation. This software exists today, I'm guessing? Yeah. What's it called? If you know.
I do know it, I'm the vendor.
Oh, you're the vendor, okay. All right. Okay. That's good, okay, thank you. Yeah, great.
You mentioned Squid, so we could install Squid locally and then use it as a...
Yeah, and it's not, so a very close friend of mine just went to a SANS training, and it's a higher level SANS course, and what you do is you work with Squid, and the end goal is that you're able to take a stream of traffic from Squid and use a Python script to export all that as a decrypted PCAP file. My buddy said it took literally the whole week to get to that point. So this isn't something from a novice to do, right? You have to have some skills and have some experience with Linux and security and Python and whatnot. So.
So I've worked with this, and I understand the need for this rigor for internet traffic to be this secure, but most of the work that we do is inside the data center. So is there as this advances, when people realize the magnitude of what you just said, is there a distinction between, is there a need for this type of rigor inside the data center? Because most of the work we do is inside, and to do all of this, I just don't see the need. And that's why I'm asking, when it advances, is cyber so worried that they need this inside a data center, that someone's going to do this server to server inside?
I'll give you two answers to that question, and I'm pretty sure there's probably 40 other people in the room that have some input on this as well. So that's a good topic to talk about, like at lunch as well. But I'll give you my 2 cents on it. Me personally, my engineer manager hat, I took that off 8 years ago, and back then my attitude was, I do not have the staff, nor the time, nor do I want to introduce encryption into my data center, because the moment any application breaks, my team is going to be called first, right? Oh, the encryption broke. Encryption's not working right. It's the encryption. It's the firewall. It's the encryption. I didn't want anything to do with that, right? And plus, I also didn't have enough clout in the organization to say, hey, we should be doing this. So, like from a real practical standpoint for me, I don't really want to go down that road. But if you look at it from a realistic security standpoint, are there attackers on the inside of people's data centers that are sitting idle? Probably. Right? Should the data be encrypted? Probably. Should the communications be encrypted? Probably. I don't know what the reality of that is. Anybody working in a data center that is tackling this specific issue right now? Yeah?
Data at rest is encrypted.
Data at rest is encrypted, yeah. That's a good idea. Data in transit, that's pretty hard to encrypt unless you have some pretty wicked gear right now. Yeah, I think that's a great conversation for later. I don't know. Do you have any thoughts on it? You?
We'll talk about, yeah, we have it at rest as well, but it's the communication. Just like you said, if it's broken, it's our fault, and we have to disprove it. And if we don't have any, and so either there needs to be another strategy for this, or everything you're talking about, in a few years, the way we do it, it won't work. I mean, we can't. I mean, it's just,
Mhm.
it could be as much work to manage these, and they're already horrific, right? Just doing it the way we do it today.
Yep.
And everything you just said today just add, like you said, it adds staff, it adds time, it adds resources, it takes years to perfect.
And what does it protect? Right? Is that now that you have all this encrypted data, is that the path of least resistance into your network? Right? Now that those paths are encrypted, you're going to go, the attacker, a smart attacker, will go find some other method, right? This is the idea behind Target's breach years ago, right? Which was a bunch of credit card data got stolen because the HVAC vendor could only have administrative privileges on the server and they had a weak password. Right, so how many millions of dollars did Target spend protecting their infrastructure with DLP and firewalls and blah, 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 and it ended up to be the HVAC system that broke it, right? So I'm the wrong guy to talk about this. Somebody can yell at me later for saying giving bad security advice, so. Don't follow my rules about security here. Okay, we should start wrapping this up. So are there any final questions? Cool? Yeah. Yeah. Cool, yeah, you're at the vendor fair, right? Are you just attending? All right, well, make sure you're gonna have a lot of people to talk to. What's your name? Randy? All right, so go talk to Randy to find out what his product does there at some point today. So I'm sure it'll be an interesting conversation. I'm looking forward to it. So I really hope everybody enjoyed this. Like I said before, this is a great conference. Use it to your advantage. If this is your first time here, do the packet challenge. Right? If this is your first time here, do the packet challenge. If it's your second time here, do the packet challenge. But if it's your first time here, do that. You know, find somebody to talk to about some of your answers. You don't want to give away all your answers, but find somebody to talk to about it so you can help yourself learn a little bit about it. It's a lot of fun, and it's well worth it. Yeah. Yeah. No, it's all so as the browsers update, everything's good, yep. Yeah. Oh, I don't know, that one I don't know. If you're interested in a free trial for Pluralsight, come up and talk to me, I'll give you a card. Otherwise, thank you everybody for attending.